We'll deal with it. It doesn't matter. All right. So hi, I'm Cassaundra Smith, and today I'm talking about build systems in general. A little bit in the Rust ecosystem. Quake is written in Rust, but I'm also talking about a project that I've been working on for the past couple months, a build system itself called Quake. So about me, I'll just real quick. Build system hacker. Previously contributed a little bit to Cargo and to Rust. I love programming languages. I love writing compilers and stuff like that. I run Uridium Consulting, which is the firm that's developing Quake. I have various links there. I'll have them later on. This is the app and dev talk. So who here writes UI apps? What about in Rust? So if you have any experience with that, you might know that handling assets or doing cross-platform stuff is really hard. Tori, for example, has solved the problem by having Cargo Tori, which does all the magic for you. But as a native feature, it's really hard to do. And this is true for lots of different languages. For JavaScript, for building for the web, there's like a million different tools that are designed to compile your assets. So yeah, cross-platform is really hard, in part because bundling makes it even harder, because now we have to target not only just things like RPMs, deb files, APKs, we also now have to do things like signing. Apple every day comes out with a new way to sign binaries, or universal binaries, where you have multiple architectures contained in one executable. And when you're building something in the native language build system, for example, Rust would be Rust-C or Cargo, really Cargo. They don't care anything about code in that language. So build.rs, it does support pre-build execution, but so far the Cargo team isn't interested in adding a post-build, which means we can't do things like different sort of asset handling stuff, or compiling other languages. So you need a meta build system on top of that to handle that. But yeah, so we're going to define some terms so we're all on the same page. When I'm talking about a compiler, we're talking about something that transforms sources into artifacts. There's all sorts of jokes online about what a compiler actually is. In this case, we're really mostly talking about files. But it is very much conceivable that sources and artifacts could be something other than, it could be text output, it could be rendering a server, whatever. It also includes things like decompilers, or for example, transpilers, Pandocs1. TypeScript is kind of that. Compilers tend to involve an element of lowering, so you're lowering down from source code to eventually down to an executable. And a build system is something that orchestrates units of compilation. Oftentimes these are very much blurred. It's not, and oftentimes we're really talking about roles here, so they overlap quite a bit. So there's different types of build systems. The sort of a naive one, it would be just task-based. So naive doesn't necessarily mean bad here, of course. I'm not putting any of these down. But things like just, where you have just files, or npm run, where you have a list of scripts, and it's basically just a bunch of things you can run command line. Most CI/CD things where you define everything in YAML, that's all just task-based. You can have conditionals and stuff. But the more interesting ones would be rules-based ones. So the OG here is make, which I have the later, but it's been around for I think almost 50 years. I think 48 years. So make, Ninja, and then the sort of collection of things like Buck and Basil, which I don't work for Meta or Google, so I don't know a ton about those. There's also Pants, which I think is an open source equivalent. But rules-based build systems are ones that perform actions informed by source artifact mappings. So I say what set of sources maps to what set of artifacts. And it's really important that we think about sets here. And we'll like find out later that like sometimes like maybe like two different things depend on the utility thing, but they also have their own. So sets can overlap, sets of sources, and then sets of sources can also be artifacts, so you can have tasks that flow into each other. So inside a compiler, you could even think of a bunch of different source artifact mappings. Like you're going from in Rust, for example, you'd be going from just Rust code down to eventually MIR, and then LLVM, and then executable. There's various domain-specific build systems. So these would be things like Cargo, CMake, Maven, I think Meson. I don't know enough about that. These all benefit from a bunch of domain-specific knowledge. So obviously Cargo and CMake and Maven and Gradle and all that sort of stuff. They actually know how the language that they're building for works. So they have batteries included. For example, in CMake, you can just do I think it's add an underscore library or whatever, find library, and that just works. The problem with domain-specific ones is that as soon as you sort of exit the domain, you're kind of in trouble. And the domain-specific ones tend to be the default. And then there's also custom ones, and this is sort of really important. This is what I was talking about earlier about Cargo, which is really just purpose-built build scripts, or maybe even an executable. So Cargo, Cargo makepad, Cargo, whatever. It's called the Cargo X-task pattern, where you basically have an alias in your Cargo config that runs an executable that is basically the equivalent of a build.sh file, which just does all of the different shell script actions that you need to actually build something. So these obviously aren't great because now you're having to rewrite it for every project probably, or at least rewrite it for every library or tool chain or whatever you're working with. So they're not very portable, and but they can be really useful too. And sometimes they're necessary. Ideally, we'd be able to integrate them with other things. So Make, we're going to talk a little bit about Make, just because I think it's pretty much the exemplary rules-based one, and it's very interesting. So it was initially developed, I believe, at Bell Labs in 1976, and it's still used today. Most people use whatever their OS version is, probably GNU Make or something like that. It has a very terse syntax, which contains a lot of magic symbols. I think most students and early programmers that look at Make files and oh my god, what's happening? But you don't even know about the advanced parts, which are even worse. It gets really complicated. There's much more, but I don't want to put it down because it really has a truly powerful set of features. And the core of it is very mathematical and algebraic. There's a blog post out there. I can't remember the name of it. It's the mathematical beauty of Make. So that math part is rules. So where you have targets, that's the thing that you're trying to build, and those have prerequisites, which are dependencies. They could be files. They could be other tasks. And then you have a recipe, which is what you actually do to achieve that target. Often, at least nowadays, Make files are generated by other tools. So you can have the autoconf for AutoTools or whatever. Or I think CMake generates Make files. Meson generates Ninja files often. So looking at a Make file, are you able to see my cursor? Oh, cool. So it's let's see. So we have wildcards. So for example, we're mapping. Actually, I'll show the syntax first. So we put the target on the left and the prerequisites on the right. So we're saying the target is an object file, and the source is a C file, and then we do all the things to compile that. I won't go into this too much. I just want to point out that this is a very common pattern. Most of you have probably at least encountered this. So these allow for a lot of implicit optimizations. So like, for example, we can use the modification time of different files, and we can look at this entire make file and look at its tree of different targets and tasks, and we can find the build tree. And using those modification times, we can compare the sources to the artifacts and determine whether or not we need to recompile. And then we can sort of go up that tree and figure out which different elements need to be recompiled. So we don't have to just redo everything, which you probably would have to do unless you hard-coded yourself. So recipes are also shell scripts. This is actually just I don't know what the default shell is, but you actually can redefine it too. And you can have multiple lines and stuff. So it's a very familiar construct, and it does sort of make sense, of course. Well, actually, we'll get into that. Also, make is installed pretty much everywhere. It's really easy to install. You probably have it if you don't use it anyway. But the disadvantages, obviously, it has a lot of magic symbols. It's difficult to read and write. It's brittle and hard to debug. For example, the whole long-standing issue with tabs, right? You have to use tabs. You can't use 4 spaces or whatever. And if you don't, you'll get some cryptic error, and then some poor student is like, "What's going on?" And they don't know how to look at the man pages or whatever. And of course, because it's shell script recipes, we get shell script problems. Shell scripts have all sorts of problems. Maybe it's quoting rules. There's tons of them. But I'll talk a little bit about Bazel and Buck. Now, again, I'm not an insider in any of these companies, so there's only so much that I can say. But these are basically in-house, purpose-built, but for the company, although they do have open source equivalents. Build systems that own the entire world. So they're aware of all the different files, all the different dependencies. When you look at a project in one of these, you see that there's just tons of different Bazel or Buck files everywhere that say, hey, this is a Java dependency, this is a whatever. So there's a lot of boilerplate, but you can write some pretty nice tool chains to let you basically reinvent Maven or Gradle, or you can, whatever you want to do. So, for example, there's a project called Reindeer for Buck 2, which emulates Cargo. So this allows for really highly optimized builds. I think Google has a whole cache server thing where they can tell based on the inputs and the environment. They can say, oh, this has already been compiled by someone with a similar machine. I'll just give you that. So when you're working on a huge mono repo at a big company, this is not a horrible idea. But it requires a lot of boilerplate, whether you move it into the projects or into a separate tool chain that you just sort of include. And like I mentioned earlier, with that old project called Reindeer, there's really just poor interoperability with outside tooling. So you don't get anything for free. You have to write it yourself. So that's a pretty big extreme. And going from sort of shell scripts where you do whatever you want, but you still have a dependency tree to you're doing everything. We really want something that's sort of a hybrid solution. And then, so some target use cases, things that we want to support with this hypothetical build system. It would be just a simple task runner. Oftentimes, if you're just building a small project, you actually just want a task runner. You don't want to worry about things like what make files have, the whole build tree or whatever. You also want to be able to, I don't know, generate cross-platform applications. You want to have multi-stage build processes. You could have a stage where you're building the cargo project, a stage where you're converting all the SVGs into PNGs. You could even do this too in parallel. That's already supported. Then eventually join them all together into a final task. So anything from a task runner to a full-fledged application builder, basically. So what do we actually want out of a build system? We want them to be very expressible, very easy to read and write, and when things go wrong, we want nice error messages. They should be pretty like self-documenting, like I would say Maven does a pretty good job of this. I'm not a huge XML fan, but Gradle also does a pretty good job of this. Like you can just look at it and you understand sort of what's going on just because it says, hey, it actually says dependencies, and it's all sort of written in like English-like syntax. We really want both simple, so like tasks, and complex, like whole dependency trees. Both of those build time requirements to be easily expressed. We also, so again, we want to be transformation aware. We want to understand source to artifact mappings. We want either this to be inferred implicitly, probably not by our tool, but maybe by a user-created tool chain, or just directly from the user input in the build script. And we also want it to be language agnostic. So I'm not gonna, like just make this just for Rust or something like that. Then also cross-platform, not just for the host, which is fairly easy, but for target platforms. Again, that doesn't necessarily involve too much on the build system side, but that is something that we want to work on. We also want it to be hackable. We want people to do weird things, and the weird things to be easily expressed as well. Like Make, as it evolved, they added a bunch of like magic features to it, and they didn't like harmonize well with the core of it. We want to be able to let users faithfully abuse the system so that they can express some complex stuff. We also want to be able to, and this is already implemented, be able to produce like machine-readable metadata based on the project and its dependencies, so that way we can get integration with third-party tooling, for example, in like your IDE, or maybe if you wanted to use Quake on like a CI/CD server, you can get a list of all the different tasks and whether they passed or failed. So more general specific improvements, we want to have better control over granularity. We want to have a more modern language. The shell scripts are not the best here. The escaping rules is honestly the biggest issue. But also there's just better things that we can do with modern languages. That helps our expressibility quite a bit. And we really want to avoid boilerplate at all costs. And we want to have a hybrid model. So the overall goal is to ensure that the easy cases are easy and the hard cases are reasonably hard. They scale roughly linearly with their complexity. So Quake, this is the actual project. It's a build system that uses Nushell as a DSL. I would kind of describe the syntax as a little bit like Gradle, for example. So it's declarative and it's self-documenting. It's sort of a hybrid of rule and task-based build systems. It's written in Rust, so it can use the Miat crate. I don't know how many of you know about that, but it's an error reporting library that lets you like point to spans and things, and have like notes and help messages, and you can have different severities and stuff. And we have all of that from Nushell already, and we can add our own. So we also have, just because of Nushell, really powerful scripting and data manipulation. I'll go into that in a second. Just a quick warning, everything here is like alpha code. I'm about to push something that'll finish up a bunch of the DSL stuff, but it's not like quite ready to try, but it's close to it. So Nushell is a functionally influenced language. It's fully cross-platform. Its main, I would say, it has like a couple like huge attracting features, but the main one is data manipulation. So when it comes to like JSON and TOML or whatever, you can just read it, and it'll convert it into Nuon, which is the internal data representation. And you can handle it like a list or like a record, or like kind of like a database. And then you can convert it back into JSON or TOML. You could go from TOML to JSON or whatever, and using the like the functional elements, you can manipulate that data. So transforming that data through pipelines, functional programming, SQL style, I guess. I actually just like stole the screenshot from the Nushell site because it was easy. But you can sort of see the syntax here. We still have like pipes, but you know, I just realized I had my there, colors are different now. You can see that we still have pipes, and then we have ways to be able to manipulate the data in that pipeline. So in this case, we have this sort of table, and it's saying where the size column is greater than 10 megabytes, and then sort by Windows modified. We can get this returns, I think, JSON. It actually doesn't matter what it returns because it'll figure it out anyway, and it'll handle it. Actually, it'll probably use the header. But we can read something from an API, or we can read something from, like, say, cargo.toml, just seamlessly, and we can get different attributes, and we can transform it in various ways. So what Quake actually looks like, we have it's centralized around a build.quake file, and it uses the def task command, which is structured very similarly to the def command, which is how you define functions in Nushell. So here we're defining a command called sayHello, takes no arguments, and then we have a do block, which is just what it does when it actually runs. In this case, we're just printing something. And then on the command line, I guess I didn't put this, it didn't end up here, but we would just write Quake space sayHello, and that would just run that. We can get a little more complicated, so we have do and where blocks. So we still have the original sayHello from earlier, but we also have like say goodbye. And inside this where block, we can use declarative or commands. It should be depends on, I updated the syntax, but we can declare that there's a dependency, say hello, and then we can do the actual evaluation. And in Quake's entire evaluation model, all of these where blocks are evaluated first. And so that means we can build up the entire tree, and well, I'll show you some examples where that's really useful later. Yeah, here's an example of purely declarative tasks that doesn't have a do block, so we just depend on checking rest format Clippy. This is just an example. You could write it lots of different ways, but if either one of these fails, then this whole thing will fail. There's also an argument that lets it soft fails, so it'll continue, but it'll it'll still check if check rest format fails, then it'll still check. It'll do check Clippy, but it'll still fail altogether. Tasks can take arguments. Like I said, def is based on how you define functions in Nushell. So, and the way you define functions in Nushell is basically like command line arguments. So here we're defining a release, and this is of type Boolean. I'm explicitly putting the type here, but an optional package and an optional target. And we can build together our arguments for cargo build. So we start with build, and if it's release, we add release. If we were provided a package, then we add target. And let me just, oh, that's so small. Goodness. How big can we make this? Okay. So, for example, and it killed my process. Yeah, so here we could actually run this with, I don't know, we could either do depends, build, and then package mylib or something like that. But on the command line, we actually can do the same thing. So the way that the arguments are structured inside the build script are able to be executed inside the build script or on the command line, which is really useful. This is an example of it. And this whole provide thing is a work in progress syntax for a way to communicate between these two blocks. So everything is evaluated programmatically. So that means we can actually have tasks that we could wrap an entire def task inside of a if block. We could wrap our depends on command inside of an if block. So we can only depend on maybe like, this is using requires, which is something different. But we could use like depends on, so if we're only on Mac OS, then depend on checking the Xcode toolchain or whatever. And that's really powerful. It allows us to construct like entire trees just through Nushell's own data manipulation stuff. So yes, sources and artifacts. Tasks themselves have a set of sources and a set of artifacts, which are actually globs, not files. And these globs are stored and not expanded. These obviously represent a transformation from the sources to artifacts, and we declare them with the sources and artifacts command. So for example, here we're just declaring that we are depending on cargo.lock and toml, and then we're just, oops, there should be an extra star there, but we're depending on all like the REST files. And we're producing a crate. And what was I gonna say? Oh, the reason why we don't actually expand the like the wild cards or the globs is that when we're in watch mode, which rebuilds parts of the build tree as things change, having the globs still be globs allows us to say if we add a new file, if I add a new .rs file somewhere, it'll actually pick that up, which is better than if we just expanded this now into all of the term files that match that, in which case you'd have to rerun the entire thing. And you see that with pretty much every watch mode implementation, or maybe 70% of them, they have that problem. So there is more granularity that we need. So if we think about like, if we're actually trying to emulate something like make, we need to be able to have more granularity of source to artifact mappings per task. So we're introducing the transforms command, which adds its own subtask with its own sources and artifacts. So here's an example with C. This translates a C file and its respective header file into an object file. This does the same thing, but it compiles onto a program. Actually, it should be -o my program here, but so these are both subtasks of build, and they will act as tasks, but they'll be mostly invisible to the user. We could still add output, but this allows us to have, again, earlier when I was talking about the hybrid of task-based and run-based, we can have a task, but it can also have its own like transformations as well, and we can do all sorts of declarative stuff here. But the problem is, this is a pretty simple thing, but the more granular we get, the more verbose we get. So we want to add automation. So let's add like functions and toolchains to help us. So one thing that Clang and GCC can do, and this is usually for make files, is that we can use the -m, capital M, is various subcommands, to essentially get make file like output. So for example, we can say, okay, food at C, like what would the equivalent make rule? And it'd say, oh, to build food at O, you need food at C, and it reads that food at C has include food at H, and it shows you that. For a binary, we specify the name, and then same thing. So we can generate these make-like rules. We can just like get them from that. There's similar things in Rust. I don't think cargo metadata quite does it. There's a couple unstable features that probably won't last, but they would allow you to do this. So we can actually parse this pretty easily with Nushell. There's lots of different ways to parse this. But taking this output, for example, we just parse the colon stuff, and then we split the rest by spaces. And then we get a record. This is normally like a fancy ASCII output, but I had to switch to, or not ASCII, Unicode output, but I had to switch to ASCII. But we can see that we get a record where the target is foo.o, and the dependencies is a list of the dependencies. And then we could turn that into a transformation. Here's an example of that. So we get the rule, and then we transform the target into the dependencies. And then we just put the GCC thing there. And then we could expand that. We could add it into a whole separate file, or put a function somewhere up here. And then we could start essentially emulating make really quickly, and with very little, just like boilerplate at all. So the main conclusions and takeaways here are that build systems need to catch up with language design. Like working on programming languages is like the exciting new thing for everyone, but like no one really pays attention to the people that are working hard on the build systems, and there's lots of features that they could have or could have better, but don't, and I would love to see that. Language designers, please do a better job, or just do something that lets you expose the internals. So earlier when I was showing the way you can get this kind of stuff out of like Clang and GCC, this is super useful. Rust should have this. Every like compiled language should have this, or not. We should be able to inspect what the actual like native build system is actually trying to do, so that we can recreate it maybe better. I encourage you to check out Quake as it develops. I'll have a link to the repository the next slide. But I also encourage you to make something better, or talk to me about ideas you have to make it better. It would be my dream for someone to beat me at it. Again, here's the links I posted earlier. The source code is on GitHub right now. There's also a source set mirror. I think it's down right now. But if you want to get in contact with me, this is my email. I'm also on Fediverse and GitHub and SourceSet, and I have a website. So yes, thank you. I'm not actually sure because we're.
Thank you.
How much time we have?
Let's take a couple more questions as usual. So thank you. So any questions for Cassaundra?
What happens if you don't specify all the sources and outputs? What is those systems?
So I'll repeat the question. Yeah. So it was asked, what happens if you don't specify all the sources and the artifacts? So for one, if you do, there is a sort of rule that if you define sources or if you define artifacts, you have to define both. Or sort of. Let me go back to the actual example. So this is more visual. Most of the time, it would just run it every time, because that's kind of the same thing to do. So basically, adding the sources and artifacts just improves the actual task, if that makes sense. Otherwise, it would just run it every single time. Adding the sources and artifacts allows you to do the modification time testing, or you could write your own rule to handle like when to skip something. So basically, it's actually adding logic to it. Otherwise, it just kind of is naive.
Okay,
Anything else?
let's take more questions over there.
Yes. So I actually have been designing the entire thing as to be a library. There's lots of different ways you could integrate it. Earlier I mentioned if you had like a CI/CD server. So there's the whole Quake engine can be used as a library. I have to improve the documentation and make all of that better. But you could totally make a Rust project that's written in Rust that uses the Quake engine, and it could do like CI/CD actions based off of that. And that's something that I want to do. So maybe look out for that in like a year or so, but we'll see.
All right, one more question?
As a follow-up to the first question, actually, and something that you mentioned at the end of the presentation, it would be nice that tools expose more of its internals.
Sorry, you're really quiet.
I was thinking about the example on your slide, check if Xcode is installed, right? So that one doesn't supply any inputs, outputs on its own. Yeah, this slide, yes.
Are you talking about this one?
Yes.
Yeah.
But could maybe check Xcode toolchain like function task itself have an output that would say like, oh, current Xcode toolchain is located at these paths, and then you can just quickly check the state of that to avoid rerunning it in the future.
So this is sort of a work in progress thing, but one of the things that Nushell has is, if I can pull this up like super quickly, it has really good error reporting. So if we do, I think it's error make, I'll zoom in so it's not horrible. So you can totally just make an error. So one time I wrote a build script which I was trying to make it so that you could build for a different platform. And instead of just having like a hard fail whenever you didn't have for example, the right Rust up target, it would actually print out and say, hey, here's where you don't have it. Here's how to install it, and then you could even prompt to make it for you. So you can totally add further logic to this. This is something that I'm expanding next.
Yeah. Just to try to clarify, I was thinking about caching the result to avoid rerunning the task.
Yeah.
So recently I saw that Xcode itself actually has this kind of built-in that once you run the script can generate a new file. That's actually kind of a make file like syntax that would then tell if any of these files have been changed, actually only then I need to run again this script. So I was thinking if this build system supports something like that in this example for check Xcode toolchain.
I'm not really sure. Are you saying you somehow make that into a source or artifact kind of equivalent? Yeah, you could do something like that. You can have alternate paths. One time I had one where there's a project cargo next test. So it has two different branching paths where it'll use cargo test if you just have that. But if you have cargo next test, it does that. And that's all included in the build tree itself. You actually can do pretty much everything already with all this because Nushell is very hackable. You can see there's the whole error make thing, so you can make errors without having to do all of this kind of stuff that I've implemented. But yeah, you can totally just flexibly change how dependencies work and change even what the concept of one is. Yeah.
All right.
All right.
Thank you very much,
All right,
Cassaundra.
thank you.
And now